Hi class, this is Mrs. Lyons, and this video will help you figure out how to determine if a covalent compound is polar or nonpolar, and then we'll go a step further to determine if what kind of intermolecular forces a molecule has. That will be in a later video. Okay, so first thing we need to think about is what does it mean to be polar? And when I think of polar, I think of polar bears who live at the North Pole or the South Pole. So poles are the opposite ends of the Earth. So that's kind of the way I think about polar. And when we talk about polar molecules, they're going to be molecules that have oppositely charged ends. And not completely charged like in an ionic compound, but partially positive, partially negative portions. Okay, so they've got a partially positive end, and we will represent that with this funky little, it's like a D, kind of reminds me of a music note, with a positive. That means that if we put that by something, it means that it's partially positive. And the partially negative, we would put the little partial and a negative sign to show that one end of the molecule is partially positive, one end's partially negative. Okay, so polarity is determined by looking at the electron distribution and seeing how much time electrons are located near one atom or the other atom in a molecule. All right, so if we think about HF, okay, hydrogen monofluoride, if you look at the Lewis dot structure of this compound, hydrogen doesn't have any lone pairs of electrons around it because remember, hydrogen only needs 2 valence electrons to be in its most stable form. Fluorine, however, has 6 valence electrons around it. So what this results in, remember, electrons are negative, so we end up with that fluorine being partially negative, and the hydrogen then, because it doesn't have any electrons by it, is partially positive. Okay, so when we have 2 atoms, it's pretty easy. One of them most likely is going to be more negative than the other. Okay, so anytime we have a binary compound, so a compound with 2 different atoms, okay, we're going to say the molecule is polar unless the atoms are identical. Okay, so for example, if we had fluorine, we know fluorine exists as a diatomic molecule, so 2 fluorine atoms bonded together. If we have F2, the atoms are identical. They're both fluorine atoms. So the electrons don't see anything different about the fluorine. So they're going to spend their time equally around both fluorines. So we call this a nonpolar molecule. All right. Now, the challenge comes in when we have to talk about molecules that don't just have 2 atoms. Okay, 2 atoms is easy. If it's one type of atom, it's nonpolar. If there are 2 different atoms, it's polar. But what about when we have multiple atoms? Okay, so there are 2 basic rules that are going to help us to determine polarity. All right, the first thing we're always going to have to do is draw the Lewis dot structure. So if you thought you were getting out, you didn't have to do that anymore. Wrong, wrong, wrong. Lewis dot structure is the starting place, and if we don't draw it right, correctly, we will not always get the right answer. Okay, so for example, if we draw the Lewis dot structure of NH3, okay, it's going to look like this. Nitrogen with single bonds to 3 hydrogens and then a lone pair of electrons. We're going to ask 2 questions to help us determine, is this molecule polar or nonpolar? Okay, the whole molecule. And the first thing we need to ask is there a lone pair of electrons on the central atom? So 2 big things. A lone pair, which we know a lone pair is a pair of electrons that aren't involved in bonding, and they have to be on the central atom. We don't care about the atoms that are around the central atom, just the central atom. Okay, so is there a lone pair of electrons on the central atom? In NH3, there is. So we're going to say NH3 is polar. Okay, now, if we have a situation where we say, no, there's not a lone pair of electrons, there's a second question we have to ask. Okay, And what that question is, we have to ask, are all atoms attached to the central atom identical? Okay, if they are all identical, that's going to be a nonpolar atom, or nonpolar molecule, excuse me. If they are not identical, that's going to be a polar molecule. So let's look at some examples. If we have the Lewis dot structure for CHCl3, it's going to look like this. Carbon attached to 3 chlorines and a hydrogen. The first thing you have to ask is, are there a lone pair of electrons on the central atom? And we are going to say, no, there are no lone pairs on the central atom. The central atom has 4 bonds coming from it, okay? Then we have to ask the next question. Are all of the atoms attached to the carbon identical? And now we're going to say no to that too. So what that tells us is that this molecule is a polar molecule. All right? Look at carbon dioxide, CO2. You've got the Lewis dot structure for it here. First question, are there a lone pair of electrons on the central atom? The answer is no. No lone pair of electrons on that carbon. Second question is, are all of the things attached to the carbon identical? And in this case, we have 2 oxygens attached to the carbon, so they are identical. What that tells us is that this is a nonpolar molecule, okay? So those 2 questions are going to kind of guide you as you determine polarity. So let's look at a couple of more examples, all right? And let's go through this. I'm going to walk you through how we're remembering how we write these formulas. So we have BF3. We have to look at our periodic table. Boron is in group 13, so it has 3 valence electrons. Fluorine is in group 17, so it has 7 valence electrons. Remember that this 3, the subscript, tells us we have 3 of those. So if we add this up, we get 21 plus 3. We have 24 valence electrons that can be included in our structure. Okay, remember when we're all done, that's how many electrons we can have. No more, no less. So we're always going to put the first atom in the center as long as it's not hydrogen. And then we're going to attach the other atoms around the side, like so. All right, now we want to get each atom so that it has an octet, so it's in its most stable form. The one thing we have to remember is that boron is one of those examples, and it is completely stable if it only has 6 valence electrons in its outer shell. Okay, so we're not going to add any more electrons to boron, but we're going to add so that fluorine, each fluorine has 8 valence electrons. We've got 6 valence electrons, and then remember each line, each of these bonds is 2. So now that we've got this structure with everything in its most stable form, let's count up how many electrons we've used. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so we've used 24 valence electrons, and I put some extra dots in there. But this would be our correct Lewis dot structure. So now we have to look at the questions. Are there any lone pair electrons on the central atom? The answer to that is no. Okay. Second question, are all of the atoms attached to the central atom identical? The answer is yes. So this tells us that BF3 is a nonpolar molecule. H2O. All right, so let's see. Hydrogen. Each hydrogen has 1 valence electron. It's in group 1. So that we've got 2 hydrogens. And then oxygen has 6 valence electrons. There's only 1 oxygen. So this tells us that we have 8 valence electrons to include in our diagram. All right. Now, remember we usually put the first atom in the center, not when it's hydrogen. Hydrogen can never be a central atom. So in this case, we're going to put oxygen in the center. We're going to put the hydrogens, 1 on either side. And now we need to put electrons around the molecules so that each atom is in its most stable form. So Oxygen needs 8 valence electrons in order to be stable. Remember, hydrogen only needs 2, so we're not going to add any electrons to those hydrogens. All right, so now let's count. We have 2, 4, 6, 8. 8 electrons in our picture. That's what we were able to use, so this is a good Lewis dot structure. Now, let's ask some questions. Is there a lone pair of electrons on the central atom? The answer is yes, not just one, but there are 2 lone pairs of electrons, which ends up making water an extremely polar molecule. And we don't have to go any farther. If there's lone pairs of electrons, then it's automatically polar. All right, one more example. NBr3, nitrogen tribromide. All right, if we look at the periodic table, nitrogen is in group 15, so it has 5 valence electrons. Bromine is a halogen in group 17, so it has 7 valence electrons, and there are 3 bromines. We add this together, we end up with 26 valence electrons that we can use in our picture. Okay, so nitrogen is going to be the central atom. It's going to be connected to 3 bromine atoms. Okay, once we've got that done, now we need to give every atom a full valence of electrons. So we're going to add electrons around so that each atom has 8 valence electrons. And we can't forget the nitrogen. It has 1, 2, 3 single bonds. It needs a lone pair up there. All right, now let's count how many electrons we have and see. Do we have 26? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 valence electrons. So this Lewis structure is correct. So let's determine if it's polar or nonpolar. Since there's a lone pair of electrons on that central atom, that makes this a polar molecule. All right, and that is it for determining polarity of molecules. I hope that helped make this a little bit more clear. I will see you in class.